mechanical translation systems. To obtain a mathematical model of a given translational system, mechanical translational system. This is the given problem, given mechanical translational system. We have to draw the free body diagram. Free body diagram. This is the free body. The free body diagram, all the forces acting on it, we have to draw. The first force is the applied force. Applied force is from left to right. Applied force is from left to right. That is marked on the free body. Then what are the reaction forces? Because of this force, the list of reaction forces are, one is because of the spring, Fk. Because of the spring, one Fk. Because of this dashpot, another force, that is Fb. The third one is because of this mass. First, we have to draw the free body diagram. In that free body diagram, this M is taken, that free body. This is the free body. In that, applied force we have to mark. That is from left to right. Left to right. Then what are the reaction? Because of this force only, there are reaction forces because of spring, dashpot, and mass. The first one is Fk because of spring. The second one is Fb because of dashpot. The third one is because of mass. There is a reaction force M. Here, all the four in the free body diagram, all the forces are marked. F of t is the applied force. Kx is the force because of spring. B dx by dt is the force because of dashpot. Then the reaction force M d square x by dt square because of mass. These are the three reaction forces. The applied force is from left to right. The other reaction forces are from right to left. So, applied force is written on the other side of that equation. The remaining reaction forces are written on the other side. That is M d square x by dt square because of mass, B dx by dt because of dashpot, and third one is Kx because of spring. That's all. This is the mathematical model in time domain. How to obtain the mathematical model in frequency domain? We have to take Laplace transform for the given equation. The Laplace transform of f of t is, the Laplace transform of f of t is f of s, and Laplace transform of m d square x by dt square is m second derivative. M second derivative, that's why m s square x of s. The initial condition is s x of 0 minus. So this is, we are assuming that the initial condition is assumed as 0 for transfer function. That's why no need to worry about this. You need not write. This also for second derivative minus dx by dt of x of 0, that is also equal to 0. Then for first derivative, b dx by dt, for that s x of s. Here also again the initial condition equal to 0. Then kx of t is written as kx of s. That's all. So what is the equation in frequency domain? F of s equal to m s square x of s plus bs x of s plus kx of s. If we take x of s outside, you will get m s square plus bs plus k. That is, x of s is the output. That is, what is assumed as output? The displacement of this body. the displacement of this body is assumed as output. Displacement is assumed as output. That's why we are finding what is the applied force f of t. Because of this f of t, there is a displacement, that is x of t is the output. This is the output. Input is what? Input is that applied force. Therefore, we have to find what is Laplace transfer function. Definition for transfer function is Laplace transform of output upon Laplace transform of input. That is the definition. Here output is the displacement x of s and the applied force is the input, that is f of s. Therefore, from this equation, we can find x of s upon f of s equal to 1 by m s square plus bs plus k. This is the transfer function of given mechanical translational system. Mechanical translational system. Here, the order of the system is second order. How we are saying that it is second order? Because of this s square in the denominator. S square in the denominator, not in the numerator. S square in the denominator, we can say that it is second order. In other words, from time domain equation also we can say that it is second order, because the main reason is why we are calling it a second order, because of second order differential equation. From that only we are saying that it is second order. This reflects in frequency domain also. That's why we got s square. That's why we got s square in the denominator. It means it is second order differential equation. Now, let us review what are the forces in that mechanical translation system. One is applied force f of t. Applied force, it is in Newton. Then displacement, that is the output. Displacement x of t, that is in meter. Then velocity v, that is in meters per second. Then acceleration, another variable. Acceleration is meter per second square. Then mass is in kilogram. And spring stiffness constant, that is Newton per meter. K is the spring stiffness constant, that is Newton per meter unit. Then for dashpot coefficient or viscous friction coefficient, that is called B. Its unit is Newton per meter per second. So this is to review what are the variables and the constants are there in the mechanical system. So for a mass, what is the reaction force? Reaction force is m d square x by dt square. That is acceleration. Second derivative of displacement is acceleration. Or we can say that first derivative of velocity. Or we can say that acceleration can be said as first derivative of velocity. In velocity form, in acceleration form, F equal to ma. F equal to mass and acceleration. We can say it this way. If you consider a spring, one end is fixed. You notice that one end is fixed, other end is free. The force is applied at the other end. The spring constant is k. The displacement is x. The velocity is v. The velocity at which it moves because of the force is v. Therefore, the reaction force because of applied force F is F of t. The reaction force, but all forces are mentioned here as F. You should understand that this is Fk. This is Fm. This is Fb. This is Fk. This is Fb. So Fk equal to k integral of v dt. Integral. So velocity, to get displacement, we have to integrate. Suppose we know dx by dt. From that, I want x means what I have to do? I have to integrate. That's all. If you integrate, what you will get? You will get x. Therefore, integral of v dt is the force exerted by this spring, or F equal to kx. The force exerted by spring is kx. If it is dash part, here also one end is fixed. In that case, v dx by dt. If you know the dx by dt as velocity, then bv. Then it is called bv. Similarly, if both the ends are free, then I said x1 minus x2, k x1 minus x2 for spring. If you know, instead of displacement, if you know velocity, integral of v1 minus v2 dt. Both ends are free in the case of dash part, then b v1 minus v2 or v d by dt of x1 minus x2, derivative of displacement, that is velocity. So these are the expressions for reaction force that we should remember to obtain the mathematical model. There is no, these are all empty because there is no acceleration form. Mathematical model of an accelerometer. Accelerometer means, already we have seen pendulum example. In that pendulum, it swings between left and right. When it is vertical, while swinging between left and right, when it is vertical, the velocity will be maximum. If it goes to the rightmost, velocity is 0. If it comes to leftmost, the velocity is 0. But the acceleration is maximum because the velocity is changing its direction. The displacement is changing its direction. That's why acceleration is maximum. Acceleration is, because of that, it is coming back. Otherwise, it will be there only. Because acceleration is not 0, that's why it's there. So that way we can understand the acceleration. Rate of change of velocity, that is acceleration. This is acceleration meter, accelerometer, to measure the acceleration. It's nothing but a small mass is placed inside, that's all. A small mass is placed inside a box. This is a box. This is a box in which a small mass is placed inside. That's all accelerometer. It has one spring. It has one spring and a dash pot. The mass has the property, or if the property of the spring, the property of mass has 0 spring constant, 0 b means we can attach additional. Like that you can imagine. So it has one mass, one spring and a dash pot it has. That's all. That's all about accelerometer. I want to measure the acceleration of your body. With that body, it is attached. That's why this line, these lines are, it is attached to a mass of which we have to find the acceleration. That's all. Here, it is attached to a mass whose acceleration has to be found. Its displacement is x. It is attached to this a car, let us assume. The displacement of that car is x. Now we have to find the acceleration of that car. The acceleration of the car can be found from this y. This y is the displacement of this mass. Because this mass is loosely fitted. One side is spring, another side dash pot. It is loosely fitted. It is not rigidly fitted to the mass box. It is loosely fitted to the box. That's why it can move. It can move. The displacement is y. Now we will write the mathematical model. From that, we can understand what is the acceleration. What are the reaction forces here? Reaction forces are Fm, Fb, and Fk. There is no applied force, that's why 0. No applied force. F of t, applied force equal to 0. That's why the right hand side is 0. Left hand side, M. The reaction force because of mass. The reaction force because of dash pot. The reaction force because of spring. What is the reaction force because of mass? M multiplied by d square, the displacement, by dt square. What is the displacement of this mass M? It is loosely fitted. If you travel in bus, if bus starts, you are standing on the bus, not sitting. Which side you are moving? Opposite side you will move in the opposite. Bus is moving to the left means you will move in the right. That's why this y direction is mentioned in the opposite direction. So net result, both are in the opposite direction. Same direction means we subtracted. Same direction means subtracted, but it is in the opposite direction. That's why it should be, what is the net displacement of this M? X minus Y or X plus Y? For spring and dashpot, we have seen that if the same direction, the deflection is x1 minus x2. We have seen, you know. For dashpot also, the displacement is x1 minus x2. But here we wrote y1 minus y minus x. Why? You see that the box is moving this direction. This mass, this M also move in this direction. How much? X direction. This is attached to that mass. At the same time, this mass moves to the right, as you mentioned, it moves to the right by a displacement of y. Now, what is the net displacement of the mass? X is moved this much. This end to this end it is moved. But because of y, it comes little bit less. What is the total displacement from this one to this one only? Can you understand this point? Not like spring. If it is spring means both are moving in the same direction. Means this is you notice that here the spring is moved to this point. Now x1, x2 is come closer. That's why the net displacement is x1 minus x2. Here the mass is moved from this point to this point. The entire box is moved. We should not say mass. The entire box is moved from this point to this point, say x. In that, the mass is little bit came this side because of acceleration. That is y. Therefore, xy, y minus x. X minus y or y minus x? We are considering y as positive. From the diagram, we can understand that y is positive. That's why y minus x. So y minus x. M d square y minus x by dt square plus b dy by dt. As far as spring is concerned, one end is fixed, other end is displacement of the mass by y. Therefore, for the dashpot, the displacement is only y. Therefore, b dy by dt. Only y. No x displacement for the dashpot. How the dashpot moves, how much? Suppose the mass is not moving. What is the displacement of the dashpot? 0. But it moves a displacement of y. That's why b dy by dt. The spring displacement is only ky. As far as mass is concerned, the mass in the space, the free body, how much it moves is important to find the acceleration. That's why it is y minus x. Not for spring and dashpot. That's all. Now you can write this x is negative. That's why you can bring this x to the other side. Therefore, m d square y by dt square plus b dy by dt plus ky equal to m d square x by dt square. But we know that we have to find the acceleration of the car in which the box is attached. That is, the car displacement is x. We are going to find the acceleration of a car. Its displacement is x. So what is the acceleration of the car? D square x by dt square. Therefore, we are interested in m, not m. We are interested in d square x by dt square. We have to find the acceleration because it is an accelerometer. We have to measure the acceleration. So ma, we can simply put ma. Here, m d square y by dt square b dy by dt plus ky equal to m d square x by dt square. For constant acceleration, the change in acceleration, second derivative of acceleration is 0. The first derivative of acceleration is constant, 0. In that case, we can assume that d square y by dt square and dy by dt are 0. If you assume like that, only ky is there. Therefore, ma equal to ky or a equal to k by m multiplied by y. K by m multiplied y. Therefore, constant acceleration is equal to k by m multiplied by y. If you know y, you can find the acceleration. Constant acceleration. What is constant acceleration? If acceleration is constant, there is no change in velocity. It remains constant. Acceleration is constant means d square y by dt is 0. Why d square y by dt square? Y is a function of acceleration. There is no change in acceleration. That's why d square y by dt square is 0. Similarly, dy by dt, that is also a function of y. Y is function of acceleration. There is no change in acceleration. That's why dy by dt also 0. So for a constant acceleration, the equation can be reduced to ky equal to m d square x by dt square. But d square x by dt square is acceleration. We can replace d square x by dt square as acceleration. Therefore, ky equal to ma or a equal to k by my. That's all. This is for constant acceleration. For the acceleration is not constant means, then it is called dynamic equation. In that case, what happens to the transfer function that we will see now? M s square y of s. I am taking Laplace transform. B y of s plus k y of s equal to m a of s. Acceleration. D square x by dt square can be assumed as acceleration. A of s. What is the output? Acceleration is the output. What is the input? Input is displacement, y. Therefore, we can find, I said in the other way. Y is the output. Acceleration is the input. For accelerometer, what is the input? Acceleration is the input. What it gives, the measurement of acceleration in terms of y it is giving. For that, the scale must be in acceleration scale. The scale must be in acceleration scale. In a voltmeter, inside the voltmeter, it deflects. Deflection type voltmeter you might have seen. Actually, what it gives, a force is developed, the needle is deflecting. But what is in the scale? It is in voltage. It measures like that. The scale is in acceleration. Therefore, y is in acceleration. Therefore, y is the output. Acceleration is the input. Therefore, the transfer function is y of s upon a of s equal to m upon m s square plus b plus k. That's all. This is a dynamic equation. Here, acceleration is not constant. Acceleration is varying. Then the mathematical model is y of s upon a of s equal to m upon m s square plus b s plus k. This is second order equation. What is the form? Whole zero form. Instead of k, if you divide the equation numerator denominator by k, it is time constant form. Here, if m equal to 1, then it is whole zero form. For that, what we have to do? We have to divide by m by m, s square plus b by m, s plus k by m. This is in whole zero form. ms square plus bs plus k, neither in the whole zero form nor in the time constant. It is in, now if you write in terms of S square, then it is in pole zero form. Mechanical rotational system. So far we have seen mechanical translational system. Mechanical translational system. Now rotational system. Translation, linear displacement, X. Rotational system means theta. It rotates. The displacement is theta. Mechanical rotational system. Here, the application is not force, torque. The application is the input energy is torque, not force. Input energy is torque. The applied energy is torque. The displacement in the spring is theta. The displacement in the spring is theta. One end is fixed. Because of the torque, the applied torque, the displacement in the spring is theta. Therefore, the reactional force is k theta. Reactional force is k theta. Applied energy is, the reactional torque is, not reaction force, sorry. The reactional torque is k theta. Applied torque is T. Therefore, these two must be equal by Newton's law. Therefore, T equal to k theta. That is the mathematical model. Here, mass equal to 0, dashpot, no dashpot effect. Mass is 0. Therefore, the mathematical model equal to k theta. T equal to k theta. That's all. If both ends are free, then that is T equal to k multiplied by theta 1 minus theta 2. Both ends are free. This displays by an angle theta 1. This is followed but by theta 2 only. Therefore, net displacement in the spring, rotational displacement is, net angle, angular displacement is theta 1 minus theta 2. Therefore, T equal to k multiplied by theta 1 minus theta 2. This is rotational system. In the same way, dashpot effect. The angle is theta. Angular displacement is theta. Angular displacement is theta. The applied torque is T. Applied torque is T. Dashpot constant is B. Therefore, applied torque must be equal to TB. That is equal to B d theta by dt. That's all. B d theta by dt. But d theta by dt is angular velocity omega. That's why we can write B omega also. B omega also. If both ends are free, one end has a displacement of theta 1, other end has a displacement of theta 2. The dashpot constant is B. Therefore, B d theta 1 by dt minus d theta 2 by dt. Why theta 1 is taken as positive? Because theta 1 is in the end in which torque is applied. The end in which torque is applied. The other end has to be taken as negative. The applied torque side must be taken as positive. Therefore, theta 1 minus theta 2. If it is both ends are free, the mathematical model is torque equal to B d theta 1 by dt minus d theta 2 by dt, or B multiplied by omega 1 minus omega 2. That's all. One more that is missing. That is, it has inertia. It has an inertia J. Applied torque is T. Displacement is theta. Displacement is theta. There, mass m. Here, moment of inertia j. Moment of inertia j is a constant. Because of mass only, it is constant. Therefore, it doesn't have any spring effect. It doesn't have any dashpot effect. In that case, the applied torque is as a reactional torque of j d square theta by dt square. D square theta by dt square, or j, if you know the velocity, d omega by dt, or j angular acceleration alpha. The or you can write j alpha. If both ends are free, that inertia, both ends are free. This end we applied a torque T. This end has a displacement of theta 1. This end has a displacement of theta 2. In that case, the mathematical model is T equal to J d square theta 1 by dt square minus d square theta 2 by dt square. Or this can also be written as J d omega 1 by dt minus d omega 2 by dt. Or which can also be written as J alpha 1 minus alpha 2. That's all. This is for rotational system. What are the constants and variables in that rotational system? Torque, the applied energy, is in the form of torque. Its unit is Newton meter. Torque is what? Suppose this is subjected to a torque of T, means the force is applied at this point. Linear force F is applied here. This is the distance x. Therefore, T equal to the torque equal to Fx. That's why the unit is Newton meter. Angular displacement is theta radians. Angular displacement is theta radians. Angular velocity is omega t radians per second. Angular acceleration is radians per second square. Linear means here what we will say meter. Linear means here meter per second. Linear means meter per second square acceleration. Here radians per second square. The moment of inertia J, the unit is kg meter square. Kg meter square. The stiffness constant of the spring K is Newton meter per second per radian. Newton meter per radian. And damping torque is, that is B, is Newton meter per radian per second. Per radian per second. That's all. So these are the, we should know the units as well as the variables and the constants used in the rotational system that we have seen. Here also we have to draw the free body diagram. What are the applied torques? We should mention. What are the reaction torques? We have to mention. Then by using law of motion, we have to write the equation. Here, one end is fixed. Therefore, T equal to the applied torque equal to the reactional torque equal to J d square theta by dt square. J d square theta by dt square. If it is a dash part, one end is fixed. In that case, B d theta by dt. Or B omega. J d omega by dt. For mass, one end fixed. The diagram is wrong. If it is spring, it is k theta. If you know the velocity, angular velocity, if you know, that is k integral of omega dt. If both ends are free, means in the case of dashpot, omega 1, b omega 1 minus omega 2, or b d theta 1 minus d theta 2 by dt. In the case of spring with both ends are free, means k theta 1 minus theta 2. If you know the velocity, integral of omega 1 minus omega 2. That's all. So these are all we should remember to obtain the mathematical model. Rotational system. We have to obtain the mathematical model. This is the given rotational system. This is the given rotational system. The applied torque is, this is some problem in rotational system. So this is the torque applied. One end is fixed. One end is fixed. Torque applied is T. The displacement, one end only. Other end is fixed. That is theta. The spring constant is K. The spring constant is K. Dashpot constant is B. The moment of inertia is J. This should be here. We can write the mathematical model. If you draw the free body diagram, J, the applied torque is T. Because of that, that end has a displacement of theta. The reactional torques are Tk, Tb, Tj. Tk is equal to what? K theta. Tb equal to V d theta by dt. Tj equal to J d square theta by dt square. So if you substitute these values, we'll get T equal to J d square theta by dt square plus B d theta by dt plus K theta. This is the mathematical model in time domain. To obtain mathematical model in frequency domain, we have to take Laplace transform. Laplace transform of this variable. T is variable. Applied torque is variable. T of S. That's all. We do not know the form of input. Torque. That's all. So we have to write T of S. If you write Laplace transform of this J d square theta by dt square, assuming zero initial condition, J s square theta of S. B d theta by theta. If you write the Laplace transform, assuming zero initial condition, B s d theta of S. K theta, if you write K theta of S. Theta is the output. Displacement is the output. Displacement is the output. So we have to find theta of S upon the input T of S. So take theta S outside, what you will get? Theta of S outside, if you take Js square plus Bs plus K. Therefore, theta of S upon T of S, the transfer function is output. Laplace transform of output by Laplace transform of input is 1 upon Js square plus Bs plus K. Js square plus Bs plus K. This is second order differential equation. Second order differential equation.